In the gilded salons of 17th-century Europe, where candlelight danced on polished wood and the air hung thick with ambition and intrigue, a seemingly trivial pursuit ignited a revolution. It was not in the sterile laboratories of physicists, nor in the hushed halls of ancient academies, but amidst the clinking of glasses and the shuffling of cards that humanity first grappled with a concept so profound it would one day hint at the existence of other realities, the very nature of probability. Consider the year 1654. A French nobleman known as the Chevalier de Marais found himself in a peculiar predicament. A seasoned gambler, he faced a problem that vexed him: how to fairly divide the stakes in a game of dice that had to be abandoned prematurely. He turned to the brilliant mathematician Blaise Pascal for a solution. What followed was an exchange of letters, not just between Pascal and his contemporary, Pierre de Fermat, but a dialogue that inadvertently laid the mathematical groundwork for analyzing alternate future outcomes. They meticulously calculated the various ways a game could have unfolded, quantifying the likelihood of each potential path, even if it never actually came to pass. This was more than just a gambling trick. It was the genesis of seeing multiple futures as quantifiable possibilities, a quiet, intellectual rumbling before the seismic shift. Yet, this nascent understanding of chance soon transcended mere numbers and dice. Just over half a century later, in the year 1710, the German philosopher Gottfried Wilhelm Leibniz published his monumental work, Essays on Theodicy. Leibniz, a polymath who grappled with the nature of existence itself, introduced a breathtaking concept: compossible worlds. These were not just theoretical constructs, but an infinite number of possible universes, each logically coherent, existing within the mind of God. Our own universe in this framework was simply the best of all possible worlds chosen for creation. This was not merely a theological musing, it was a rigorous, logical exploration of combinatorial possibilities, a cosmic permutation of all that could be. The intellectual challenge of quantifying random events and rationalizing the universe's very being thus led humanity to conceptualize a vast, unseen landscape of possibilities. This was a proto-multiverse, forged not from subatomic particles or cosmic inflation, but from pure, unadulterated reason. Leibniz's elaborate framework, though rooted in divine philosophy, was fundamentally a profound logical exercise. It demanded an understanding of how myriad elements could combine to form distinct, internally consistent realities, setting an intricate stage for future scientific inquiry, even if he could not have foreseen its form. The question was no longer simply what is, but what else could be. Observe the surprising, almost poetic link that binds a gambler's rolling dice, a philosopher's contemplation of God's infinite wisdom, and the relentless modern scientific quest for other realities. The core driver, the engine of this intellectual progress spanning centuries, remains a simple yet profoundly powerful question: what if? It is a query that has propelled human thought forward, from the dusty salons of the 17th century to the cutting-edge quantum laboratories of today, long before the advent of quantum mechanics even hinted at the bizarre nature of our own existence. It is a testament to humanity's enduring fascination with the unseen, the unchosen, the roads not taken. The intellectual journey that began in the gilded salons of 17th-century Europe, where philosophers contemplated abstract possibilities and gamblers sought to quantify chance, took a dramatic and unforeseen turn in the mid-20th century. The pursuit of alternate outcomes suddenly moved from the realm of pure reason to the cold, stark reality of engineering, driven not by curiosity about the divine, but by the urgent, existential threat of a world plunged into a new kind of war. This was not a theoretical exercise, it was a matter of survival, where the very concept of parallel realities was accidentally forged in the crucible of atomic power. It was in the classified facilities of Los Alamos, New Mexico, during the frantic years of the 1940s, that the first practical engines for exploring alternate realities began to whir. Here, within the top-secret confines of the Manhattan Project, the brightest minds gathered to unlock the secrets of the atom. Among them was the Hungarian-American mathematical genius John von Neumann, a figure whose intellect cast a long shadow over the nascent field of computing. His task, alongside Polish-American mathematician Stanislaw Ulam, was not to ponder philosophical universes, but to predict the terrifying, unpredictable behavior of subatomic particles at the heart of a nuclear weapon. The challenge they faced was immense. How do you control a nuclear chain reaction, a cascade of events where one neutron could strike multiple atoms, each collision spawning new neutrons, each with its own chaotic trajectory? The number of potential paths and interactions a single neutron could take within a fissile core was astronomically large, far beyond human calculation. This problem was so complex, so riddled with inherent randomness, that traditional analytical methods simply failed. Von Neumann and Ulam needed a new approach, one that embraced uncertainty rather than attempting to eliminate it. Their solution was ingenious, almost deceptively simple. They developed what is now known as the Monte Carlo method. This computational algorithm, named after the famous gambling city, models future outcomes by running thousands upon thousands of randomized simulations. Instead of trying to calculate every single possibility, they would simulate the life of a single neutron again and again, each time letting it follow a different random path dictated by probabilities. Each of these simulated journeys, each unique sequence of collisions and decays, effectively represented a tiny, self-contained, parallel history of that neutron's existence within the atomic core. For these groundbreaking simulations to be feasible, unprecedented computational power was required. Enter the ENIAC, the electronic numerical integrator and computer, a colossal machine, one of the world's first general-purpose electronic computers. This monumental device was not some sleek, desk-sized gadget. It was a behemoth, weighing in at approximately 27 tons, equivalent to the mass of nearly 5 fully grown African elephants, and occupying an entire room, spreading across 1,800 square feet of floor space. Its immense processing capability, though primitive by today's standards, was revolutionary for its time, capable of performing 5,000 additions per second, a speed that felt like magic to the scientists of that era. The ENIAC became the engine for these early multiverse explorations. It crunched numbers tirelessly, generating countless hypothetical scenarios of neutron behavior. By analyzing these thousands of tiny, parallel histories, scientists could determine the most probable outcomes, understand the statistical behavior of the chain reaction, and ultimately calculate how to control it. The goal was to understand where the neutrons were most likely to travel, how many would trigger further fissions, and whether the reaction would fizzle out or explode with devastating force. This was not about finding alternate versions of ourselves. It was about ensuring that the atomic age, once unleashed, could be managed, or tragically, weaponized effectively. It is a profound realization, the very concept of multiverse simulation, an idea now often associated with cutting-edge video games or complex climate models, did not originate in a playful attempt to model virtual worlds. Its true birth lay in the gravest of human endeavors, the desperate need to understand and control atomic power during the Cold War, the necessity of predicting chaos, of mapping the myriad potential futures of subatomic particles, inadvertently forged one of history's first practical engines for exploring alternate realities. This crucial tool, born from the geopolitical landscape of global conflict, fundamentally linked the abstract idea of parallel worlds to the dawn of the information age, demonstrating how humanity's greatest fears often inadvertently drive its most revolutionary scientific advancements. In the mid-20th century, as humanity grappled with the raw, untamed power of the atom, the very fabric of reality itself began to unravel, not in the destructive force of a nuclear reaction, but in the elegant, perplexing equations of quantum mechanics. For decades, physicists had peered into the subatomic realm, a world where particles behaved less like solid objects and more like elusive ghosts, existing in multiple states simultaneously until observed. This was the measurement problem, a profound enigma at the heart of quantum theory. What exactly happens to a quantum system when it is measured? What forces it to choose one definitive reality out of a cloud of possibilities? The dominant answer, championed by the revered Danish physicist Niels Bohr and his colleagues, was the Copenhagen interpretation. This view posited that the act of observation, of measurement, somehow forced the quantum wave function, the mathematical description of a particle's potential states, to collapse into a single, definite outcome. It was a pragmatic solution, one that worked beautifully for predicting experimental results, yet it carried an uncomfortable, almost mystical implication. Reality wasn't fixed until we looked at it. A tiny, arbitrary act of observation seemed to wield immense cosmic power, dictating the very existence of what we perceive. Into this perplexing landscape stepped a brilliant but quietly iconoclastic young American physicist named Hugh Everett III. It was the 1950s, and Everett, then a doctoral student at Princeton University, found himself deeply troubled by this arbitrary nature of the wave function collapse. He saw it not as an elegant solution, but as a blemish on the otherwise pristine mathematical purity of the Schrödinger equation, the cornerstone of quantum mechanics that precisely described how quantum states evolve over time. The equation itself never hinted at a collapse. It always maintained all possibilities. Everett's landmark 1957 Ph.D. thesis, titled Relative State Formulation of Quantum Mechanics, was not a wild, speculative flight of fancy, despite its radical implications. On the contrary, it was a profoundly conservative and logical attempt to save the fundamental integrity of quantum mathematics. He refused to introduce an external, unexplainable process like collapse into the elegant framework of the Schrödinger equation. Instead, he simply followed the math to its logical, unsettling conclusion. If the equation says all possibilities exist, then all possibilities must continue to exist. His revolutionary idea, which would later be known as the many worlds interpretation, proposed that every time a quantum measurement is made, every possible outcome of that measurement does happen. Each outcome, however, occurs in its own distinct branching timeline. So, when a quantum particle could be spinning clockwise or counterclockwise, and we measure it, the universe doesn't pick one. Instead, the universe, and everything within it, including us, splits. One branch experiences the clockwise spin, another experiences the counterclockwise spin. The universe, in Everett's vision, is not a single, linear path, but a perpetually growing, unimaginably vast tree of parallel realities, each new quantum interaction spawning countless new branches. This concept, so elegant in its mathematical derivation, was met with intense intellectual isolation and skepticism from the established physics community. They found it too extravagant, too counterintuitive, and too untestable. His own mentor, the renowned physicist John Archibald Wheeler, a man who had initially encouraged Everett's radical thinking, arranged a fateful meeting with Niels Bohr in Copenhagen, hoping for a breakthrough. But the encounter went poorly. Bohr, deeply entrenched in his interpretation, was reportedly dismissive, unwilling to engage with a theory that challenged his life's work. The sheer weight of scientific orthodoxy descended upon Everett, leaving his groundbreaking idea largely unacknowledged for years. Hugh Everett III didn't set out to create a multiverse. He was not pursuing a fantastical vision of alternate selves or parallel dimensions for the sheer thrill of it. His motivation was far more fundamental, a deep-seated desire for mathematical consistency, for a quantum theory that did not require a mysterious, undefined collapse mechanism. He was a reluctant creator, forced by the logic of the quantum realm to conceive of a reality far more expansive and bewildering than anyone had ever imagined. His work suggests that every decision we make, every quantum fluctuation, isn't just a path taken, but a moment when the cosmic tree of reality bifurcates, creating an uncountable number of other yous, living out every conceivable alternative. Gaze into the cosmic abyss, back to the very first slivers of a second after the Big Bang. For decades, our understanding of the universe's violent birth painted a picture of rapid expansion, but it was a picture with two glaring, almost embarrassing flaws. These were the universe's most profound puzzles, cosmic anomalies that hinted at missing pieces in our grand theory of everything. 1. Why is the universe so incredibly flat, like a perfectly leveled billiard table stretching for billions of light-years? Any slight deviation from flatness in the early universe, even by 1 part in a quadrillion, would have caused it to either collapse back on itself immediately or expand so rapidly that no structures, no galaxies, no life could ever form. And 2. How could the most distant corners of the observable universe, separated by billions of light-years and seemingly never in communication, be at almost precisely the same temperature? It was as if two people on opposite sides of the Earth, who had never met or spoken, somehow knew to wear the exact same sweater on a given day. These were the flatness and horizon problems, paradoxes that lingered in the equations of cosmology, undermining the elegant simplicity of the Big Bang model. Then, in 1980, an American physicist named Alan Guth, then at Stanford University, stumbled upon a truly radical solution. He wasn't even looking for it. He was grappling with an entirely different problem related to exotic particles called magnetic monopoles. His insight, later refined by cosmologists like the brilliant Russian-American Andrei Linde, proposed a new, mind-bending phase of the early universe, cosmic inflation. It was not just an expansion, but an exponential expansion, a burst of growth so unimaginably swift and powerful that it dwarfs any other event in cosmic history. This inflationary period, lasting for perhaps only a tiny fraction of a second, a mere 1/1,000,000th of a trillionth of a trillionth of a second, or 10 to the power of minus 36 seconds, saw the universe expand by a factor of at least 10 to the power of 26. To grasp this scale, consider inflating a speck of dust, smaller than the smallest atom, to the size of our entire observable universe. Such an incredible runaway expansion would iron out any initial wrinkles or curvature, just as inflating a small, crumpled balloon to a size larger than any skyscraper would make its surface appear perfectly flat to any observer on it. This explains the universe's uncanny flatness, transforming a cosmic enigma into a logical consequence of an ultra-rapid growth spurt. Furthermore, this hyper-expansion brilliantly resolves the horizon problem. Before inflation began, all the matter and energy that would eventually become our entire observable universe was packed into an incredibly tiny region, a space so small that light, traveling at its immense speed of nearly 300,000 kilometers per second, had more than enough time to cross it, allowing all parts to reach a uniform temperature. Then, inflation took hold, stretching this minuscule, thermally homogeneous patch into the vast cosmos we inhabit today. The distant regions we now see, which appear causally disconnected, were once intimately linked, their thermal equilibrium set before the universe exploded outwards in its inflationary surge. Yet, here is where the concept of a singular universe begins to truly unravel. While inflation started, and then abruptly stopped in our own region, allowing our cosmos to cool and form stars and galaxies, what if it didn't stop everywhere else? This is the profound idea of eternal inflation. It suggests that the inflationary process, once initiated, might never entirely cease throughout the entirety of the vast, overarching cosmic landscape. Think of it not as a single, uniform expansion, but as an ever-churning, bubbling foam. Each bubble that pinches off and stops inflating becomes its own distinct universe, cooling down and evolving its own unique history. Our universe, with its billions of galaxies and countless stars, is simply one such bubble, a relatively quiet pocket in an eternally expanding metaspace. The implications are staggering. If this cosmic foam is indeed real, then an infinite number of other bubble universes are constantly being born. And here is the crucial distinction. These other universes are not merely duplicates of our own. The random quantum fluctuations that seeded the initial conditions within each bubble would mean that fundamental physical constants, the exact strength of gravity, the precise mass of an electron, the speed of light itself, could be radically different in each one. Imagine a universe where gravity is 1,000 times stronger, where atoms can't form, or one where light travels at the speed of a snail. The very laws of physics, the rules governing existence, might vary wildly from bubble to bubble, creating an unimaginable landscape of cosmic possibilities. This cosmic lottery makes the existence of an identical you in another universe, down to every memory and every freckle, extraordinarily improbable. It is far more likely that any other universe would be utterly inhospitable to life, or even to the formation of stable matter as we know it. This leads us to the anthropic principle, a concept that asks a provocative question. Why are the laws of physics in our universe so perfectly tuned to allow for life, for stars, for planets, for consciousness itself? If there are countless universes with different laws, then our universe's life-friendly parameters are not a special miracle or divine design. Instead, they are a simple consequence of selection bias. We exist in this particular universe precisely because it is one of the vanishingly few bubbles where the physics allowed for our existence. We are not here because the universe was made for us. Rather, we can only observe a universe that allows us to be here. After journeying through the boundless cosmic foam of eternal inflation, where entire universes bloom like countless bubbles in a grand, ever-expanding metaspace, and after wrestling with the perplexing quantum realm where reality itself seems to split and multiply with every subatomic measurement, the grand, almost terrifying question remains: what does any of this mean for you? For your identity, your choices, your very existence? Perhaps the most profound answers are not to be found in the unfathomable distances between galaxies or the elusive dance of quantum particles, but in the most intimate, yet still largely mysterious, 3 pounds of matter nestled within your own skull. This is the human brain, a biological marvel that in its silent, ceaseless operation acts as its own astonishing possibility engine, ceaselessly simulating its own micro-multiverse. Consider a seemingly simple moment in your day, the instant you choose between 2 different options, perhaps which route to take to work, or what to have for dinner. What truly happens within those intricate folds of gray and white matter? Neuroscience reveals that your brain does not merely select one path and discard the other. Instead, specifically within the highly evolved prefrontal cortex, a region crucial for planning, decision-making, and complex thought, your mind rapidly constructs and models the potential consequences of each available path. These are not mere abstract thoughts. They are fleeting, ghost realities, fully simulated scenarios of what could happen, played out in intricate detail within your neural networks, complete with predicted emotional responses and potential outcomes. This remarkable ability to weigh hypothetical futures is deeply rooted in our cognitive architecture. The work of pioneering neuroscientists and behavioral economists, such as the Nobel Prize-winning Israeli-American psychologist Daniel Kahneman, whose groundbreaking prospect theory reshaped our understanding of human choice, highlights just how complex and often irrational this process can be. Kahneman and his collaborator, Amos Tversky, demonstrated that when faced with a decision, we do not simply assess objective probabilities. Instead, our brains emotionally and irrationally weigh potential gains and losses, often overestimating the impact of negative outcomes while underestimating positive ones, creating a subjective landscape of desirability for each simulated future. This deep-seated bias shapes the very ghost realities our brains generate, influencing which path ultimately feels most appealing or least threatening. This internal simulation process is not just a mechanism for immediate decision-making, it is a fundamental cognitive tool for learning and planning, deeply entwined with what psychologists call counterfactual thinking. This is our innate tendency to imagine, what if? What if I had taken that other job? What if I had said something different? This mental exercise, far from being a mere idle rumination, is how we extract lessons from past experiences, both our own and those we merely imagine. By replaying past events with different choices, our brains refine their models of the world, preparing us for future challenges by effectively creating a mental archive of alternate histories, each one a unique learning opportunity. The capacity to envision these unchosen paths is so powerful that it allows us to learn from mistakes we never actually made, adapting our behavior based on purely hypothetical scenarios. What this profound internal activity suggests is a radical reinterpretation of our subjective experience of reality. The linear, singular timeline we perceive, the sense that we are moving inexorably from one fixed moment to the next, is in many ways an elaborate illusion. It is a brilliant construct created by consciousness to allow us to navigate a world teeming with infinite quantum possibilities and countless practical choices. Your brain, in essence, is perpetually collapsing, a wave of potential futures, selecting the one that it will then present to your conscious awareness as the singular, unfolding present. This active, ongoing process transforms the very nature of the multiverse from an external, cosmic phenomenon to an internal, deeply personal cognitive process. We are not just observers of a potentially branching reality. We are, each and every one of us, natural-born simulators of alternate worlds, constantly generating and then narrowing down the boundless landscape of what could be. What if the deepest secrets of our universe aren't etched in stone, or forged in the crucible of a quantum split, but written in code? For centuries, scientists and philosophers have grappled with the fundamental nature of existence, progressing from matter and energy to space-time to the very fabric of possibility itself. Now, the most cutting-edge frontiers of physics suggest an even more mind-bending truth. Reality might not be about physical worlds at all, but about something far more abstract, yet profoundly tangible: information. Delve into a concept that redefines everything: the provocative idea that the universe, with all its galaxies, stars, and living beings, emerges from bits of information. This revolutionary hypothesis, often encapsulated in the profound phrase, "it from bit," was first put forth by the late American physicist John Archibald Wheeler in the 1980s. Wheeler, a towering figure in physics who coined the term black hole, suggested that every physical entity, every law of physics, every particle, could ultimately be derived from yes or no answers, from the most fundamental binary choices, much like the ones and zeros that form the bedrock of our digital world. This wasn't a mere poetic musing. It was a radical assertion that information might be the most irreducible component of reality, the primary ingredient from which everything else springs forth. This audacious perspective gains startling traction when confronting one of the most vexing puzzles in modern physics: the black hole information paradox. When matter, Whether a star the size of 1,000 suns or a single atom crosses the event horizon of a black hole, it appears to vanish forever. According to classical physics, any information about its original state, its precise chemical composition, its temperature, its quantum properties, would be irrecoverably lost, leaving behind only the black hole's mass, charge, and angular momentum. However, this outright destruction of information fundamentally clashes with the bedrock principles of quantum mechanics, which assert that information can never truly be destroyed, only transformed. It is like deleting a file from a computer. Even if you can no longer access it directly, the data still exists somewhere on the hard drive, encoded in residual magnetic patterns. The black hole paradox therefore represents a profound conceptual crisis, a cosmic wrestling match between two of our most successful theories of the universe. The search for a resolution to this paradox led to one of the most groundbreaking and counterintuitive concepts developed in the 1990s, the holographic principle. This principle, largely pioneered by the brilliant Dutch physicist Gerard Hooft and the insightful American physicist Leonard Susskind, offers a potential way out of the black hole dilemma and, in doing so, radically redefines our understanding of space and reality. To grasp its essence, consider a standard security hologram, the kind you might find on a credit card or a banknote. From a flat, two-dimensional surface, a complex, three-dimensional image appears to project into space, shifting and changing as you view it from different angles. All the information needed to reconstruct that intricate three-dimensional image is encoded, not within a three-dimensional volume, but on a two-dimensional surface. The holographic principle posits that our entire three-dimensional universe, with all its depth, galaxies, and seemingly infinite expanse, might be a similar projection. It suggests that all the information describing our universe is not contained within its vast volume, but rather encoded on a distant two-dimensional boundary, a cosmic surface at the edge of our reality, much like the flattened data on a cosmic hard drive. This boundary would hold every detail of every particle, every interaction, every thought that has ever occurred or ever will occur within our perceived three-dimensional space. The universe, in this view, is not a solid, tangible place in the traditional sense, but an emergent phenomenon, a sophisticated illusion rendered from a deeper, two-dimensional informational substrate. If this astonishing theory holds true, what then becomes of the notion of parallel universes? They might not be distinct physical spaces in the way we traditionally conceive of them, separate cosmic bubbles floating in a metaspace, as suggested by eternal inflation. Instead, they could be understood as different files or configurations within this grand cosmic information system. Imagine a colossal universal hard drive containing not just one version of reality, but countless distinct datasets, each representing a unique universe with its own history, its own physical laws, and its own inhabitants. These alternate realities would not be spatially separated, but rather informational variations, different patterns of data existing within the same overarching cosmic code. This perspective profoundly reframes the question of whether an other you exists. It suggests that an alternate version of yourself might not be a separate physical being residing in a distant parallel world, but rather an alternate informational pattern, a different set of data points in the universal code. Every choice you didn't make, every path not taken, could exist not as a branching universe, but as a different configuration of bits on that cosmic hard drive. Your past, your present, your potential futures are all just data, awaiting their readout in this informational cosmos. It is a universe where reality is not a fixed stage, but a perpetually re-rendering simulation, running countless versions of existence based on the most fundamental units of information. What truly defines you? Is it the very atoms that compose your body, the memories etched into your brain, or the unique sequence of choices that have unfolded across your lifetime? As we have explored the vast and bewildering landscape of the multiverse, from the ancient philosophical whispers of infinite possibilities to the Cold War simulations of alternate futures, from the quantum mechanics that split realities to the cosmic inflation that births entire universes, and even the informational code that might underpin existence itself, a profound question inevitably arises, one that strikes at the very core of our being. If other yous truly exist, are they still you? Consider an ancient paradox, a thought experiment that has baffled philosophers for more than 2,000 years, the ship of Theseus. The legendary ship, upon which the hero Theseus sailed, was preserved by the Athenians for centuries. But as its wooden planks decayed, they were systematically replaced, one by one, with new, identical pieces. The question that haunted the minds of thinkers from Plutarch to Thomas Hobbes was this: once every single plank, every mast, every nail had been replaced, was it still the same ship? And what if the old, discarded planks were then reassembled to form a second vessel? Which of these two ships, if either, would be the original ship of Theseus? This is no mere academic riddle concerning ancient timber. It cuts to the heart of identity itself. Now, apply this age-old puzzle to the most intimate subject imaginable: yourself. What if, according to the tenets of quantum mechanics, a mere second ago, a subtle subatomic fluctuation caused a tiny, almost imperceptible branch in reality? In one timeline, you chose to read this sentence. In another, an almost identical you, sharing 99.999% of your entire history, every memory, every experience, every single atom, made a different, infinitesimally small choice. Perhaps they paused for a breath slightly longer, or blinked at a different microsecond. Is that person, that nearly indistinguishable echo of yourself, still you? And if not, what precisely separates your consciousness from theirs? This thorny problem of personal identity, especially when confronted with the dizzying implications of a multiverse, occupied the brilliant mind of the British philosopher Derek Parfit in the 20th century. Parfit argued against the rigid, intuitive notion of a strict, all-or-nothing identity. Instead, he proposed that what truly matters is not a fixed, unchanging self, but rather psychological continuity. This means that the links that connect you to your past self, your memories, your intentions, your character traits, your desires, are what constitute your identity, even if your physical components change over time, or if slight variations occur across parallel timelines. It is less about being the exact same thing, and more about the unbroken, evolving chain of experiences and mental states. So, the notion of you is not a static noun, a fixed entity cast in stone at birth. It is, instead, a dynamic verb, an ongoing process of information, experience, and memory. Your consciousness is a unique, unfolding pattern, perpetually shaped by the cascade of decisions, both grand and infinitesimal, that define your path through this particular reality. Every thought, every feeling, every interaction you have adds another brushstroke to this ever-changing portrait of self. In this profound light, the existence of other yos in countless parallel universes, whether those universes are physically real or simply a powerful metaphor for the boundless computational possibilities, becomes less significant than the astonishing realization of the sheer improbability and inherent preciousness of this specific pattern of consciousness. The one experiencing these words, right here, right now, in this universe. It is a singular, intricate tapestry, woven from billions of years of cosmic evolution and trillions of neural connections. And the journey of understanding that unique tapestry, that dynamic verb of being, has only just begun.